Well, thank you very much for that introduction, and I want to also thank my colleague Erin Moore, who initiated our speaker's visit here tonight. And this is, for me, a great opportunity to welcome back Professor Steve Lansing, who hired me here at USC, along with my colleague Janet Hoskins. And then, I have to tell you, he left USC and went off to live in Singapore. But in between that, he was an emeritus professor of anthropology at the University of Arizona. He is currently also a senior research fellow at the Stockholm Resilience Centre, an external professor at the Santa Fe Institute and the Vienna Complexity Hub. And as if that wasn't enough, he is also the president of the Anthropology and Environment Society, a branch of the American Anthropological Association. His recent research has to do with adaptive, self-organized criticality I really needed to put this in bigger letters, in coupled socio-ecological systems and co-phylogenies of languages and genes in the islands of Indonesia. And this is where some of our mutual interests overlap. I've worked on islands in Papua New Guinea, so we've had many conversations over the years about islands and island ecologies. In 2012, he developed a UNESCO World Heritage site for the subaks that we're going to be hearing about in his talk today, and water temples, the networks in Bali. Just very briefly, before he moved to Arizona after he had left USC, he held joint appointments at the University of Michigan in the School of Environmental Natural Resources and Environment and the Department of Anthropology. And as I mentioned, he had been here earlier and had chaired the anthropology department. He's been a fellow at the Institute for Advanced Study at Princeton, the Center for Advanced Study in the Behavioral Sciences at Stanford, the Institute of Advanced Study at Durham University in the UK, and the Eichmann Institute for Molecular Biology in Jakarta. So I think that you can tell from this wide variety of institutes and organizations that Steve has been involved with over the years that he has done groundbreaking research in issues of complexity and looking at human and non-human environments and their interrelationships. So I know a number of you who are here who know his work on priests and programmers, one of his early publications about his work in Bali. So we're looking forward to his talk today, Hidden Order, Lessons from Bali's Water Temples. So Steve, it really is a pleasure to welcome you back.
So here's my story. This is a book I've just finished for Princeton Complexity series. I'm an anthropologist. I've been spending a lot of time in these islands over the years, and the title is meant to refer to islands, you know, places where the sea breezes rustle the palms, but also islands of order in the mathematical sense of attractors, and I'll get to that in a minute. And the reason I'm interested in complexity, I spend about half my time, I direct a complexity institute in Singapore. I spend a lot of time working with people, mostly physicists, on complexity. So the question one might ask is, why would an anthropologist be interested in or even need to interact with physicists with the kinds of models they think about, and you're thinking about anthropological questions? I think we actually need to do a lot more thinking about those topics because we, Western social scientists, people like me, have made a lot of mistakes. And I think those mistakes have to do with not recognizing what we're seeing. And complexity, for me, has been a way of revealing things that have surprised me. So the first part of this talk will be a story about something which I hope you'll see is an interesting revelation, maybe. And then the second part is about the invisibility of these Balinese institutions and what we're trying to do, we're thinking about, to make them visible in order to make it possible for them to survive. So first part, you know, what use is complexity, basically. It's very fashionable. It's kind of, in a way, it's sort of past its shelf life thing, I think. It's been a fad for too long, the notion of complexity. But my message will be that actually there really is something to it for us social scientists. So begin with this illustration. So here we are on our water planet, and you know, how much is there? That's how much water there is in the planet. That's how much fresh water. And half the world depends upon rice. And rice needs lots of water. It's also the most important, it's the largest source of greenhouse gas emissions of any of the agricultural plants. So you need to think about how rice is grown, how it works. And rice needs not only water, but it needs to be very carefully managed. So Lynn Ostrom, when she got her Nobel Prize in 2009, it was awarded for her analysis of economic governance, especially the commons, common property systems. And her focus was on the rules by which they are governed. She compared different systems. She liked to work in Nepal, but she also liked Bali. She was interested in Bali. It's one of her favorite examples. So the question is, how is this system managed? It's done from the bottom up, not from the top down. So how does it work? You know, it's kind of an interesting mosaic. How does that pattern emerge? In Bali, it's organized by institutions called subaks. So a subak is a group of farmers who share water from the same source and who meet to decide how they're going to manage that water, that gift of water, regularly in water temples. They've been doing this since the 12th century. We know that because there are inscriptions that start referring to them about that time. So here's a subak meeting. These guys are getting together and they're talking about one of two things. It's either the management of the ecology of the rice terraces, or it's organizing the rituals that will take place to thank the gods and the goddesses for this gift of water and indeed of life. They're pretty small, average size about 40 hectares, about 80 farmers. They vary, but they're small face-to-face groups of people. Briefly, the engineering goes like this. Bali is a wet tropical volcanic island, steep slopes, and so the rivers flow in deep channels because the rainfall on the volcanic rock picks up little minute pumice particles and slices channels down the slopes of the volcanoes. So you need to get the water somewhere that you can plant it, you know, that you can have level fields. From the 9th century, the Balinese have been building irrigation tunnels. So they build a tunnel down in the ravine and angle the water out. It emerges maybe a kilometer or more downstream like this. And then here's the water going to two different groups of subaks. And here's a shrine where the farmers can come and give thanks for the gift of water at that little shrine. So actually a couple subaks arriving here. And then finally the water comes down and it waters these terraced fields, all built by hand. Timing is critical because you need to flood the fields at first, and then as time goes on, they're dried. And the timing of that irrigation schedule determines not only what's happening in your fields, but how much water is released for your downstream neighbors. So because there's so many subaks, you know, kind of cascading down these volcanic slopes, water sharing is the big question for management. It has to be shared. Here's a typical river. You can see it's just down on the bottom of a ravine, not like a nice flat Californian river. So there's a different engineering challenge. In addition to delivering the water to flood the fields, farmers also can control pests, the things that like to eat the rice, which can be rats or mice or bacterial and viral diseases that are spread by insects. But they can be controlled by flooding. So this large area has been flooded at the same time, nothing growing. They've removed the habitat for the pests. And if you look at that picture, this is all, you know, these are held up, these buns really. This is made of earth, held together with hoes and the active labor of the farmers. It looks, the Balinese will say it looks like a jewel when it looks like this. But if you stop managing it, if the guys up there stop managing the flow of water in their fields, pretty soon it doesn't look like a jewel, it looks like a muddy slope. So there's a need for active cooperative management to make this thing work. In 1975-76, the Green Revolution had just begun. The Green Revolution means the introduction of Western farming techniques, basically. It's high-yielding plants that are designed to grow quickly, along with chemical fertilizers and pesticides. So this came as a package to the Balinese farmers. The farmers were told, in the interests of national development, take this new rice and plant just as fast as you can. If you can get 3 crops a year, great. Some of the old people said, well, the trouble with that is, according to our traditional system, we schedule, we carefully time when the water goes into the fields and when it doesn't, and there are reasons for that.
After a couple of years of bumper harvests, those reasons started to become clear. Stephen Lansing's old friend, Wayan Pege, is a farmer in Sebatu. He remembers what it was like 20 years ago when the pests began to appear.
Waktu sekitar tahun 80-an tuh dah diulang lagi.
The Green Revolution remedy for pests was pesticides. It's not just that the farmers were advised to use pesticides, they were forced to use pesticides. They would be punished by the government if they didn't, because the government would say, if anybody doesn't use pesticides immediately, as soon as any sign of pests appear, then the pest will spread to other fields. So within a year or two, even the farmers, pumping these pesticides into their fields couldn't kill all the pests. The government then began to fly the island, dropping pesticides from airplanes, and they succeeded in killing damn near everything.
Itu kepercayaan tetap fungsinya kepada Sang Pencipta, karena segala yang hidup itu ditentukan oleh Sang Pencipta.
He says that everything is made by a creator, and so by disturbing anything, by killing anything, you're disturbing part of the creation. So you need to pay attention to the whole picture. Essentially, he's saying you have to pay attention to the whole picture.
Wow.
Yeah.
Wow. And that, Stephen told me, was the role of the water temple. Looking at the whole picture, applying wisdom accumulated over centuries.
In the middle courtyard of the temple, the farmers gather every month. They make decisions in a democratic assembly on how they're going to plant. Okay, but how does it actually work? They can get together and manage things at the scale of subaks, but we were talking about many subaks along the slopes of the volcanoes. So how, in fact, do they actually manage to get the water to the right place at the right time? So here we are with Google Earth, just taking a little picture of the landscape. So these are villages, and these patches are the rice paddies, okay? Kind of a mosaic. Put this into a GIS, and these colors, which are different colored areas, indicate different stages or ages of the rice plant. So we get a kind of a mosaic pattern which looks pretty chaotic, right? And the question is, does it have any meaning? Why that pattern? So we take one subak, that guy, that's one subak, and ask whether it is independent or whether it actually interacts with the other subaks in some important way. In other words, is it part of a larger system or is it a single unit? So here's a model, very simple model, just to see how that could work. So here we are balancing the pest-water trade-off, which means, trade-off means to maximize the amount of water that is shared, you want to have everybody plant at different times. But if you want to maximize removing the pests, you want large numbers of subaks to plant at the same time. But what each group does upstream affects the conditions downstream. So it's a pretty complicated problem. And it's changing all the time because the weather's changing. So here's a model. Each of these little dots is a subak. And the color is an irrigation system, schedule, rather. So maybe blue means, plant in January and in August, and yellow means plant in February and in September, something like that. Just some arbitrary collection of cropping patterns. There they are. So now we've got our subak here. The color indicates the cropping pattern they've chosen, and they've just compared their harvests. At the end of the year, the harvest will be calculated based upon how much water damage or pest loss has happened based on the interactions right in that lattice. So red got the best harvest. That's us. So we choose red for our cropping pattern next time. Everybody does that, and then we try it again. So here's the beginning. Colors of the irrigation schedules, it's random. And the consequence will be many pests because after one harvest is over, the bugs can flee to the next field. They can just sort of hopscotch all over the place. So that's a recipe for growing lots of pests. That was the Green Revolution, okay? But what happens because of the adaptive logic we've just put into this, that you're going to start comparing with your nearest neighbor that has the best harvest, as time goes on, patches emerge. So this blue patch is a little bit larger. There'll be fewer pests. And you'll notice that the size distribution of patches is pretty uniform over the whole system. So I thought I understood the system at that point. We've got lots of individual subaks, and each one is balancing that trade-off. But the model kept going. The model didn't stop. Even though it did improve the harvests, this is what appeared. And I was mystified because that patch is too large and that patch is too small, right? According to what I've just told you, how is it that that overall system could do a good job of managing both the water and the pests? Well, the logic of the computer, I mean, in fact, the harvests rise, and what we discover is that the relationship between harvests in these patches becomes correlated. So I'll explain what that means, what it means in just a moment. It turns out that it's Pareto optimal at that point. What that means is no one can get a better harvest for himself by changing, and he cannot, any change in this system will cause someone to have a smaller harvest. So it's kind of a victory for cooperation to achieve optimal harvests, not just for me and my subak, for everybody. So how in the world could that possibly happen? That was the question. So here's the evolution of this system. First it's random. Within about 8 years, 8 cycles, you get lots of little patches. But then it always goes to this, and then it stops. No more changes occur, because everybody's at a local optimum. That's a phase transition, because here we've gone from many local systems, each autonomous, to one large system in which they're connected, but they're not all doing the same thing. They're connected, but they're not all doing the same thing. So that looks to a physicist very much like the phenomenon of magnetism. So if you want to create a magnet, then you have particles, right, that can be magnetized, and at high temperature, they're random. They can spin up or spin down, and the spins will be random as long as the temperature is high. But as you lower the temperature, then they begin to clump together. So these are all spin up, and those are spin down. And the system evolves. At a certain point, the correlation between these, which I'll explain in just a moment, they become correlated. They're no longer independent, not just within the patch, but across all the patches. And at the phase transition, they become a magnet. It's just at that point that this becomes a magnet. If you continue to lower the temperature, then it will become more and more magnetic. Actually, the patches will become larger, and in the end, they'll all be either spin up or spin down. Doesn't happen quite the same way here with the subaks. Here we are comparing the subaks with the magnets. The subaks get to the critical point, and then they stop. They just stop. These guys will keep evolving. The transition point is really not important for them. That's where magnetism starts, but then magnetism will continue to grow. It's reversible. If you heat the magnet, then gradually the will be lost, and these patches will become uncoordinated, uncorrelated. So what's going on? Well, here's the comparison then. It starts out in both cases with random patches, goes to many patches, and then finally to one system. So we tried this many times, and it worked every time, at which point we thought, okay, could this possibly have any relationship to what really happens in Balinese rice paddies? Because this was the simplest physical model we could build, or actually I could build. So here's the transition at the critical point in the magnet. It's reversible. Here's exactly the transition point for the subaks, and that is Pareto optimal in the model, meaning nobody can do any better by changing. They all stop changing. Okay, so does this only happen in the model? Okay, here's the interesting thing about this thing. This is the distribution of different size patches, and this is their size. So there's a big patch here, and then there are sort of more medium-sized patches, and there are lots of little patches. Okay? They fall along a line. That's a power law relationship. It's a regular relationship. Okay? So we find power laws happen for many reasons, but we notice that there's one here. what's intriguing is, here's the correlation and distance. That means you pick any place here, and you say how correlated is the blue here to the next, to the next, to the next, across this whole system. And that too follows a power law, meaning you're very closely correlated with your near neighbors, and that diminishes, but it encompasses the entire system. So that happens to be from a Google Earth image from the region of Tamanan in 2002. Let's try another. Here's Gianyar in 2013. Well, the distribution in patches is still a power law, and so also the correlation distances. So that's mimicking the model. Here we are, in other words, that looks like a phase transition. And here we are in Klungkung in 2015, same pattern. And here, after 13 cases, okay, is the cumulative distribution. Here's the model size frequency of patches. And the red is Gianyar, and here's all the subaks. And over here, the correlation distances between the model and the Google Earth images. We quit after 13 because it takes a long time to code these things. We said, okay, it does look like it actually works. So this is in PNAS a few months ago, May, I think it is. So the actual dynamics in the model we can analyze. This is the correlation length, varying depending on how strong the water stress is and the pest stress, meaning how much damage is caused. In the model, we can tune this. You know, we can make the pests very damaging or less damaging. If they are equal, if they balance, then we get to the phase transition. They have to, in other words, this doesn't always happen with pests and water. It happens when the pest and water damages are the same weighting, same force. And here's the real data. It falls right there. So it looks like something's going on. It looks like it's really a phase transition, and it means that these systems are correlated in this way. Okay, so let's say that's true. Assume for the moment that this could be true. So then you have to ask the question, how did they manage to maintain that structure? Because staying near that phase transition requires cooperation by lots of people, right? And that takes us to the next step here, which is the goddess of the lakes and the relationship between the farmers. At the center of the island, close to the center, there's a volcano with a crater lake. There's the volcanic peaks. And there's the lake where the goddess of the lakes dwells. And according to Balinese belief, she is the one who bestows water on the island. The lake is actually in a bowl. There are no river outlets. There's no irrigation system coming out of the lake. It does feed the groundwater system, but symbolically, it is the origin, the source of water for everyone, every farmer. Every year, the full moon of the 10th month, just about now, everyone who grows rice and uses that water sends delegations up to the temple of the goddess on Mount Batur, where they bring the things that grew in their fields, and in return they receive a token blessing of holy water, indicating the receipt of that gift by the goddess. Here is one of the temple scribes writing invitation letters on Balinese palm leaf manuscript. He's telling people what to bring and what date the festival will occur. So it's like a letter of invitation. Here he is writing it. And here's a guy from North Bali who's representing his subak. He's the elected head of the subak, and he's reporting in, saying, okay, we brought our rice, we brought the things that grew in our fields. May we have our holy water, okay? And so he's given this thing. It's a bamboo tube wrapped with some money around it. It's called a sujun. And he's got a little ticket. There's so many people that they have to actually organize it with tickets, okay? So he's waiting for one of the temple priests to go up, collect water, which was collected from the springs around the lake, token of the blessing of the goddess and the subsidiary deities. That is going to go to, it's going to be handed over to the head of the subak, and he will now take it. Here he is leaving the temple, down to his subak, where he'll pour it into a vat in the temple. They'll add more water from temples in the region, indicating the blessing of the local gods and goddesses, and then everybody gets a cup. Like if we were a subak, you'd all get a cup of that water, which would have at least a little drop or two from the lake, and you sprinkle it on your field, the upstream edge of your field. That happens every year, connects everyone to the water temple, connects the whole system, all of the water, all of the all of the subaks, all of the temples. It's the apex of the network. Here's the high priest of the temple. These are big offering containers where we actually put a token of the things that grew in our fields. So he's explaining why they do that, in case anybody forgot. Pula Kirti, the origins of goodness. Why are we, why do you do this? People are told, this is why. And here they are, putting their rice from their field and celebrating Pareto optimality, right? Because this cooperative system works, right? It works. This is the temple as it was in 1917. So off about where I am is where the lake is. And there's the volcanic cone. We're still in the bowl of the volcano. And there's a wall of lava which had come down a few years earlier and stopped within 1.5 meters of the gate to the temple. Astonishing the Dutch colonial officer who was there at the time, because the temple was protected. And here are the dancers, the traditional dancers of the temple. Around the temple there were structures created by 6 of the kings of Bali, where they too would participate in these rituals. The kings did not claim, no single king claimed to own it. They all, however, acknowledged a responsibility to patronize, to make their own offerings. So there they are, 1917. And here they are in 2014. This continues, same dance, same temple, although now the temple has been moved to the rim of the crater because a subsequent volcanic eruption buried the village under a lot of lava, but not too quickly, so they were able to move the heirlooms up to the rim. Interestingly, from about the 14th century, as this subak system expanded, gradually the institutions of kingship disintegrated in Bali, leaving feudal lords, but none of the apparatus of kingship, little of the apparatus of kingship that we see in the early phase of the development of Balinese kingdoms, quite unlike the island of Java nearby, where they do not have a subak system. Okay, so here we are. Here are people bringing the offerings to that temple.
Once the government understood this, they allowed the water temples to regain control. But the Green Revolution still lingers. To this day, farmers add chemical fertilizer to this ancient, self-sustaining system.
For the last 30 years, the farmers have been borrowing money from the village cooperatives to buy fertilizer that they don't need, applying it to the fields. It washes out of the fields immediately, flows back into the rivers and down to the sea. This little stream is flowing right out of those rice paddies up there. And as it comes down, it's of course carrying all the mineral nutrients from the volcanic soil, plus all that fertilizer. I mean, all the fertilizer that wasn't needed by the farms and is just washing down. So by the time it gets here to the sea, it's like a thin nutrient soup. And so the effect is you grow simple organisms like algae, the algae that you see growing along the rocks there. And that's what we find offshore, just blanketing the coral reefs. And we only find it in places like this where you've got that kind of agricultural drainage. On the rest of the island, if there's no river carrying fertilizer, then the reefs are fine. But out there, the reefs are nearly dead. Computer models helped us convince the government that the water temple rituals, the rituals of the subaks, were not purely religious, that they had functional importance. So that was good, and there's no longer any opposition to management of irrigation by groups of subaks and those rituals. However, that solved one problem, but meanwhile, they're still being told to buy this commercial fertilizer and put it on their fields. And so as you see, it flows down and it delivers far too much nitrogen to the sea. So in the next little clip, I'm going to show you we're on an offshore island. We're just off the coast of Bali, where there is no irrigation system. It's a small island. And comparing the condition of the reefs with the reefs that are at the, within the agricultural drainages. In other words, where that dose of fertilizer is happening every few months. What Murph tells you is that the reefs are perfectly fine on around the offshore island where there are no agricultural drainages, but around the island, the closer you are to the outlet of the rivers that are carrying the fertilizer, the more algae and the the less healthy the reefs are. So in other words, the farmers are wasting their money buying pollution, in effect, because that relationship wasn't understood enough.
Here we have seen massive colonies of tabular or table coral, these acropora table corals, some of them the diameter of this boat, and they're in perfect health. Whereas on the mainland we also saw some pretty large corals, but most of the large ones were dead. And so that tells us that in the past the conditions were such, the reef was healthy, and those big corals lived long enough to really grow to a substantial size. But they're not alive now, so something's changed.
So this is the point I'm trying to make here, is this system was invisible. We're making lots of mistakes. We social scientists, we consultants, because we don't understand these systems. We need to work harder at understanding them. But I'm going to turn now from that story about Bali to the question, what do we do? So the Balinese have been coping with the after effects of the Green Revolution and also globalization and tourism. They sent in 2009 a delegation to Paris asking for World Heritage status from UNESCO, and that is a subak ritual taking place to the astonishment of the French in the UNESCO headquarters, making that request. They also brought an orchestra, and UNESCO was charmed, but they didn't get their World Heritage, and indeed, like the previous 4 attempts to create a World Heritage in Bali, this one failed. However, in 2013, UNESCO said yes, and there is now a World Heritage in Bali, the cultural landscape of the subaks and water temples of Bali. But when they made that announcement, they also warned that it may almost be too late. So there's a certain urgency about kind of getting on top of the management system. And the problem for guys like him and him, these are the elected heads of their respective subaks, is how can they manage tourism? How can they manage the influx of visitors? How can the powers of the subaks, which are designed to control things in a Balinese way, be extended to control the, basically globalization on the island? So our solution to this was to simply empower a governing assembly of the subaks. Subaks are always led by elected leaders. There are always elections, and it's a religious offense to cheat, to steal from a subak. So I've heard all kinds of things about corruption over the years in Indonesia and in Bali, but not about corruption in these traditional institutions of the subak and the traditional village. It's a religious offense. It's too dangerous. So, as UNESCO observed, Balinese really don't need to be taught how to manage their landscape in a democratic way. They've been doing that for centuries. So here's the notion, here's the World Heritage as it exists now. It consists, here's the lakes, here's the forests, and then the red area are subaks. This is the largest part of the World Heritage, but we had to pick several different locations to try to encompass the system. So up here is the Temple of the Crater Lake, the one I just showed you, where the most important temple, and there's that lake. Down here are 3 subaks, where the earliest irrigation systems, we think, came into existence. And this is basically the early kingdoms of Bali here. And finally, one more temple down here that we had to include because it belongs to a very powerful ruler, and it does have something to do with water temple, but it isn't really, shouldn't be there. Anyway, it's there now. Okay, so here's our system. When UNESCO agreed to create the World Heritage, they empowered, as far as they were concerned, they empowered the governing assembly of the subaks. That didn't happen. Those of us who wrote this nomination document and made the design to manage it were taken gently out of the management system. And there were new meetings held. Consultants were brought in to say, how should the Ministry of Tourism cooperate with the Ministry of Religion, et cetera, in managing our new World Heritage? So they had lots of meetings. Farmers were not invited to those meetings. And in fact, we created a monster. We created a top-down system of management instead of the one that we were trying to create. So it's been frustrating for the last 5 years. But a new phase has begun. Just recently, the farmers have basically revolted. They say they won't go to any more of these meetings, and they're going to pass a law in the region of they're going to pass a law empowering themselves with the support of the head of the culture department. So it looks like there's a possibility for a solution. And that takes me to how to do it. How could it be managed?
My name is Julia Watson and I'm a professor here at RPI, where I'm teaching a design studio where the students are looking at designing for the new World Heritage landscape in Bali. The key problem for the villagers is how to cope with the foreign visitors. And with over 1 million visitors to Bali each year, the landscape is literally in danger of being loved to death. We want to bring some design concepts directly to the 21 villages inside the UNESCO World Heritage landscape. What would the Balinese people like to share with their visitors? We're creating designs for lots of projects like visitor gateways, museums, and interpretive walks. And we want to give control back to the villagers of the design process.
So the idea is manage the World Heritage using basically technology. Everybody has a cell phone. Cell phone knows what language you speak and where it is and what time it is. So using apps that have been developed for heritage management and outdoor museums by Johns Hopkins and various other places, put those together so that tourists somewhere in Bali say, heard about an interesting World Heritage, I think I'll go there. Go online, and what you find there is an invitation from the World Heritage, in other words, from the people. What would they like to invite people to participate in and see? So you sign up, okay, for the first 80 people or so to come to the Barong Festival at Kut, or the Gamelan rehearsal, or the this or the that, right? Your name goes on the list, and you check off the box whether you're going to have lunch, all those things, right? All that can be managed with the phones. Then when you get there, your phone can know where you are and what you're looking at. So to some level, we think we can have some augmented reality so that you get some clue about what's going on. This removes any opportunity, we hope, for corruption, because the money just goes, it's like making a hotel reservation or a restaurant reservation. You just, you'd buy your ticket and then there you'd go. So with this device, we hope it may be possible to empower the governing assemblies to manage the World Heritage. Anyway, that's what we're working on now. So, and here's Julia with her eco-museums and visitor gateways, all kinds of resources that could be made available to visitors as much as they wanted or needed to see with respect to what they could learn from the World Heritage. Of course, for me, this is a very enticing possibility because we could tell stories like the one I began this lecture with. Bali, I think, is a very interesting example of a complex adaptive system. You wouldn't probably notice it if you hadn't heard my 15 minutes on that subject, but if we did it properly, we could show people something about how all that works, what those rituals are about, what the colors of the offerings mean, all those kinds of things. So in this way, we think it should be possible to give the subaks to restore their control for their landscape, which at the moment is it's very chaotic, very frustrating for them. And maybe rescue this system at the last minute. Now, I come back now, I'm about to wind up with the problem here was this system remains invisible. This has been, for me, this research has been a series of discoveries about how things work that are otherwise hard to see, right? Like all of the examples that I've given you. So in this way, perhaps we can help different aspects of the subaks become visible, actually not only to Korean visitors, but also to Indonesian school children, right? Some of this is not so obvious. Okay, so to achieve visibility at last, this is a diagram in the Indonesian language. Finally, raises the question, do systems like this exist elsewhere, right? Could there also be, if we have farmers engaged in farming, in other words, playing games with nature and with each other to which nature responds, does that set in motion some kind of dynamic of cooperation that might lead to structures like the ones we just saw? We just started, got a couple of students who they think they found something similar in the Philippines. Open question, you could look anywhere you aim Google Earth, you can look at a landscape and you could, if you could code the patches in that landscape, which is a relatively simple thing to do, then you can ask the simple questions we asked about patch distribution, frequency distributions, and correlations. And in fact, we provide all that code in the paper. So we're hoping that people are going to start looking for and discovering these systems elsewhere. So, conclusion of the talk is this process of adaptive self-organization has got something to do, surely, with the centuries of harmonious cooperation that if I took you to Bali next week, you would see in the temple. That's what's about to happen again. Thousands of people over 10 days. This research has been done over many years with many colleagues, all of whom are acknowledged in the papers. I won't read their names here, but they're all part of that. I just want to say a couple of things just in conclusion. What goes on now, this is Sharda, who's measuring the greenhouse gas emissions from the rice paddy. There's a group at University of California, Davis, that's discovered that by manipulating the irrigation schedule, you can reduce both nitrous oxide and methane emissions by about 80%, just managing the irrigation. So we're just now, starting to do that. And then there are kind of broader questions. This region, Indonesia, this archipelago has the highest biodiversity, both terrestrial, Sumatra and Borneo and so forth, and also marine. But with the destruction of the forests and the conversion of the remaining lands to oil palm plantations, Indonesia has become the third largest carbon emitter after the US and China. And that's not from little motorcycles, that's from the burning of the forests of the richest biodiversity on the planet. This is renewed research on the coral cores, from which you can not only trace the pollution from the fertilizer, but further offshore. I should back up one thing. This region is where the Indonesian flow-through meets this mass of water from the Pacific. The INSO El Nino system moves through here, so the water gets pushed in between these big islands, and it flows through here. So the coral grows at about 1 centimeter a year, and from the isotopes that you can find in that coral, you can get a history of temperature and salinity, basically changes in the climate. And if you happen to have it in the Lombok Straits, then you're looking at the intersection of the two great oceanic masses that occurs there, so you can learn something about land-ocean atmosphere coupling. Seems like an urgent question. 2 graduate students are pursuing it at the moment. We're not paying enough attention to the things that really matter. This finally, last slide, just in case anyone's interested. So I've painted a picture of harmonious cooperation, and that's largely true in Bali, or the subak system would not exist. But sometimes subaks fall apart, sometimes they fail. Some are more cooperative than others. So what we're doing here is trying to look at the dynamics that differ between the cooperative and the uncooperative subaks to see under what conditions do they fail. So this attractor is, most of them are very cooperative. These are 2 different ones in which they're less cooperative. These are the variables that just come out of a simple questionnaire. Say, how good is your subak at making decisions, okay? And what you see here is that the responses vary. This attractor, their problems are dominated with social problems. These guys, it's ecological problems. So there are ways in which one can do that, kind of pulling apart I was trained to just use simple surveys and take the average results and do statistics. That's not good enough because things are different. And what you really want to find out are what are the dynamics that cause these systems to vary and to be different? And if possible, what are the transition paths that would lead from one attractor to the other? All completely doable. The system I've described is agricultural. This is also very much known that the phenomenon that I've just described to you, the change to the patch distribution until it becomes correlated, also has recently become recognized as a frequent phenomenon in in non-agricultural ecologies. But there's a crucial difference. These patches, you can see they're different sized patches of vegetation, but they're all the same kind of vegetation. So they're not, the differences between them have no functional significance. Whereas with the subak system, the differences between them indicate what's happening with the water. So there is something different about that. But the basic phenomenon of a change, indicating a change in the level of control, is common to both agricultural and natural systems, like savannas. Okay, that really is the end. Thank you very much.